he is responsible at Broadcom for the development of low-power solutions for cellular systems on the chip. His current research interests include system architecture level power modeling, estimation, optimization, power thermal management, architecture and algorithms, and low power design methodology for battery-powered mobile system on chip. He has published more than 15 technical papers and articles as a first author, both in journals and conferences, including such conferences as TVLSI, TCAD, DAC, DATE, ISLPD, etc. There is low power design and power thermal management architecture. He has worked in the semiconductor industries during the last 15 years, holding various positions at Broadcom, LG, Samsung, and Intel. Dr. Jung received his PhD in electrical engineering from the University of Southern California. He is a member of IEEE and has been serving on the technical program committee of ISQED since 2008. So, let's welcome Dr. Jung.
Thank you, Dr. Jung.
To those who are trying to follow this two solution, I would like to remind you this, first of all, at our experiments, this, for the first time we are trying to show the presentation files. So the first thing you have to do is to find on your wireless network a specific network called IEEE 02. When you have connected to this network, you have to enter a specific internet address that unfortunately I cannot see from here. So the address should be HTTP. So they should not ask you for security. Well,
it doesn't ask for a password. It just open. You've got to find it. It's hidden as well. So
that's strange. Well,
I found it, and then I select there's nothing happening. I'm still not connected. Any magic?
But you were able to connect, I guess, to the previous tutorial, right?
I just select that, but there was no connection.
that's right. It's a private.
Let's put on USB.
Okay, we will check very shortly what's going on the I'm not sure this is the best way to proceed because you see sharing stick. Yeah, it works for your computer, but what if you have a virus? Then your virus will spread throughout the whole classroom. So let us wait until student back and we will check if the router is really working. So this could be a problem. Let us start with the being and I will take a look what's going on there.
Okay, so sorry for the inconvenience. Thank you all for attending this meeting. This is the last session of today's program, people reception. So I'll make it simple and I'll probably finish in like 1 hour. Then I will have a 10-minute Q&A. Okay, so today I'm going to talk about some power and thermal. I'm sorry for the harsh voice because I have some suspect. Okay, so I'll talk about some power and thermal challenges for the smart white device. So to last few days at CES, you've probably seen the lot about a smartphone and the wearable device. Actually, these are one of our hot key in this year's CES because people are bringing up to the new, the fancy smartphone and the wearable device for the going forward. So I believe this is a new technology trend for the upcoming year. And although it looks simple for the smartphone and wearable device, there's a lot of power and thermal challenges for this. So I'd like to talk about some challenges for this, and I'd like to introduce some solution to minimize power and tackle the smart issue. So I'll start with some background, and I'll talk about mostly in the power and thermal challenges for the smartphone. And last, I'd like to cover what will be the challenges for the wearable and white devices. So this chart shows the smartphone growth worldwide from 2009 to the projected 2015, so you can see still the smartphone segment growth with a lot of key enabling technology like LTE and 5G Wi-Fi. So if you look into the inside the smartphone, there's a lot of some IC components, so-called system on chip. So these system on chips are designed specifically to meet the market need. For example, there will be NFC and combo chip like includes Bluetooth and Wi-Fi, and GPS and cellular, something like that. So what the market needs is kind of a small form factor because there's levels of pressure to minimize the total cost of bill of material for the smartphone. So we're trying to integrate or to measure functionality like application processor and GPU and 2G with a modem inside a single SoC for to meet the market needs. So there are a number of these SoC designs are specifically driven by some requirement from the manufacturer or some visual perspective. So there will be the power or performance or area and thermal. So do we need to install just one of the power and performance area or thermal to design this SoC, or just focus on the power performance area, not the thermal? For the competitive mobile device, we need to consider this requirement at the same time for the competitive mobile device in the market. But here in this tutorial, I'll focus on the power and the thermal issue. But these are very closely related to we cannot separate this like the performance area outside of this story. But here I like to focus on the power and the thermal, mostly on the smartphone and the wearable mobile device. So during the last decades, the performance has increased a lot to satisfy the users, the kind of functionality to satisfy the user needs. Like application has been developed a lot with a higher frequency, like more than 1 gigahertz or 2 gigahertz. And you can see a lot of dual core, quad-core, hexa-core inside the single SoC. And you can see a lot of performance increase for the application processors inside the smartphone. Similarly, now you can see the CS Lemon. It's a huge fancy graphic processing by using the OpenGL ES 2.0, 3.0. Like a standard also evolving for the better feature inside the smartphone. You can see now you can see the 4K, the video resolution through the TV, and hopefully you can see the smartphone as well. Similarly, the mobile, the data rate is increased a lot. You can see like the LTE around the 200 megabytes per second in some smartphone in the market. So if you consider like some major features inside the smartphone, estimated around the 2020, we can see that some performance has increased around the 20 to 30x performance increase. But you can see still around the 2x increase for the battery capacity, which means that extending the battery life with the smartphone while guaranteeing the performance requirement will be the challenging. So this is one example of how low power feature is very important compared to the performance and the area. Now the thermal issue. So now assume that we have an application processor, GPU, and modem. As you mentioned before, if we increase the performance of this, like multi-core configuration, more than 2 gigahertz speed, and for the GPU, like 1080p, now it's 4K, more than 60 frames per second, and LTE, LTE8 in the future, then higher power consumption will be higher because of higher performance. And higher performance means a higher junction temperature. Then we need to consider the thermal because without thermal management technique, we will see we call the skin temperature of the smartphone being large, so there's some damage for the hand or the skin like that. So we need to consider thermal issue at the same time while we're developing the power management technique. So as you mentioned, the high power means the high junction temperature. And what we see is high junction temperature. The first, we see the leakage power. So, okay, there will be some dynamic power and leakage power, but mostly the leakage increase exponentially while the chip temperature increase. And then there will be the thermal runaway issue. So what is the thermal runaway? Because this is a junction temperature of the silicon is a function of the power, which means that when higher temperature, you will affect the increase the junction temperature, which means the total power consumption will be increased, and as a result, the junction temperature also increase. It's kind of a loop over here, which means that there could be a thermal runaway. Higher temperature increase high power, and as a result, is a high temperature. So we need to consider thermal runaway. If you don't have any management technique or some solution that your chip or phone, the temperature will be increased here. And this is some cross-key issue due to the thermal gradient, which means that, for example, some part of the ICs are some cooler than the other area, which we call it the thermal gradient, which will affect the cross-Q. I mean that if you have a silicon, there could be some malfunctional, so functional error. And from the silicon relative perspective, there will be the degraded gate oxide lifetime issue and the thermal stress over time. This picture shows that the capacity available inside the silicon due to the thermal stress is kind of a major issue. So now we have to consider the thermal issue at the beginning of the design of the SoC. Now from this slide, I will cover the power challenge, thermal challenge, and then last I will cover slightly about the wearable mobile device. So first, power challenge. So as you mentioned before, if you look into the SoC, there will be major IP like modem, functionality, and application processor, and some GPU, and some various analog IP. Because this integration is visible because we are designing the silicon on the nanotechnology like 40 nanometer or 20 nanometer. So you can actually integrate all the IP inside the single silicon. Then you can see a lot of multiple power domain. So this is a survey at 2 years ago by the synopsis by more than more than 600 customers on the how many clock domain do we use inside the actual silicon, and then how many power domain do we use inside the SoC. So you can see that this bottom line represents in general SoC, but if we consider the mobile segment, you'll see more than 20 clock domain. This is at the 2012. If you look into the current state art, the SoC, you will see probably more than 40 or 50 different clock domain. Similarly, instead of mobile SoC, this is a survey at 2 years ago. Now, if you look into the state art of SoC, you probably see more than 30 or 40 different power domain inside the SoC. Because we have a more different IP with a different functionality, and then we can put more power domain to better utilize the power management technique to minimize power consumption. So more power domain, and you can use the various low power technique to minimize power consumption. So there will be the power gating and the clock gating, very simple, and kind of a run fast and shut down, which means that if you look into the below the 40 nanometer or 28 nanometer technology, the power will increase a lot compared to the dynamic power increase at the fast silicon at the high temperature. So there is some technique like run fast, the processing, then shut down the power gating. Then you don't see any leakage power after that. And adaptive voltage scaling technique and widely known the dynamic voltage and frequency scale technique. And there's a lot of low power technique that you can use inside the SoC with the multiple power domain to minimize the power consumption. So this slide shows the first challenge from the power perspective. So I just mentioned that there's a lot of technique to minimize the power consumption. But to capture the exact power saving opportunity, first we need to estimate the power consumption very accurately at early stage. If you have a certain proton number, it's kind of a garbage in, garbage out, so we should have accurate power number at the early stage. And this estimation could be done for some system level perspective, system level use case, like what is the power consumption for the deep sleep mode, and what is the MP3 playback power number, and 1080p video playback. Because when you buy a phone, like some Apple, Samsung phone, you probably seen like some number in the box, like 1 week standby time or 10-hour video processor like that. It is a kind of a market means, and then we have to consider the system level use case when we estimate the power followed by optimizing this power consumption. Then the most important thing is there's a lot of, maybe I'll talk about it later again. So we need to consider the process and the voltage and temperature variation at early stage because it's hard to estimate accurate power due to this phenomenon. So this slide shows some level of the power estimation during the SoC and the system level, the platform design, with some accuracy and positive opportunity. So, and it is widely known that we can estimate accurate power number at the gate level simulation, but it's not accurate at the high level because we have some rough number. But on the other hand, we can capture the great power saving opportunity at the system level compared to the gate level power estimation flow. And there will be some number of the consideration. For example, for the gate level power estimation, we need to consider the factor. It's kind of a time-based factor. And we need to consider the process, voltage, and temperature to have accurate leakage power and the dynamic power as well. And then if you look into some higher level, you can see some different consideration. But the system level, as I mentioned before, we are typically interested in the power consumption for the use case, like MP3 playback or video playback. And by using those power management IC, we have to capture what is expected battery life. So if it's not, sometimes like some smartphone company like some Apple and Samsung, they have a requirement. When estimated this power number is not satisfied, then we need to find out what is the power saving opportunity, what is the technique. Then we can devise the best optimal low power technique in early stage. Because if we found this number and later on, it's too late to change the architecture or the implementation strategy. There's a reason we need to capture accurate number at the higher level, like the system level at early stage. It's very hard to get an accurate number because we are usually using the proton number if we don't have any detail of the gate level simulation data. So how can we tackle this scenario? The simple way is to bring the accuracy of the gate level up to the system level by using the IP power model. For example, at the gate level, we can build a power model with actual silicon measurement data or the information data, like what is a standard cell, its configuration, like low threshold voltage cell or high threshold or standard voltage cell, or what is the gate length and what is the supply voltage, something like that. So based on this, we can build with this is an equation for the substrate leakage. At the same time, we can build the dynamic power. So after this, we can build as a parameterized because at the architecture level, sometimes we need to scale. Like what happens if we have a 500 megahertz or the 1 gigahertz at the one board? So this could be a scaling parameter for the dynamic and leakage power. And similarly, for example, plug-in efficiency. Assume that we have a active mode and a standby mode. We assume that, okay, standby mode, there could be no switch activity. So we believe the dynamic power should be 0. But sometimes, there is assumed that the clock gating is applied with 100%. but it's not true at the design time. We can assume around 70% and 80% because of some design constraint. We need to have some, what is a clock getting efficiency, where we can see some clock power, although there's no switch activity inside the design. If we have some IP level block, then we can bring up to this SoC level. So this is kind of a parameterized IP and SoC level. So at the system level, based on the use case, we can define the actual, the voltage and frequency for each IP, the SoC component inside the platform, and we can consider the software over here. Because if you look into inside the Android power management technique, there's a lot of some API like CPU idle or CPU loss. We need to consider this issue while optimizing the total power consumption. So there is one example of how we can build a better power estimation flow by bringing the accuracy into the system level. So we can capture great positive opportunity during the early design stage. So second challenge is about how to tackle the increasing level of the process, voltage, and temperature variation. This graph shows the standard deviation of the threshold voltage and number of dopant atom across effective channel length. Maybe we can assume that this is something like a technology law from the 140 to the 20 nanometer technology. Like, if you look into just the standard deviation of the threshold voltage, if you look into the below the 40 nanometer, you can see the standard deviation is increased a lot, which means that there's a lot of process variation. The process variation actually affects a different number. For example, now we have a silicon at the typical corner. When we measure the leakage, probably you can see more than 2x or 3x chains. Although it's the same type of the silicon at the room temperature. So this indicated that we have some difficulty in optimizing power consumption during the power optimization stage. So what will be the solution? So our solution is to change operating voltage based on the process and the temperature variation. This is called adaptive voltage scaling technique. Now assume that, so this is a voltage level and the silicon process. Assume that this is okay. So first, for those of you who are not familiar with this, when we manufacture the silicon, there will be a typical or slow and a fast property, because although we manufacture from the silicon, there is some process variation. So we call the fast or slow, but most of the silicon we are getting is a typical process. This is called the process of the corner case. Okay.
If you're going to build a device with a lot of different power domains, and let's suppose your battery is a 3-volt battery, and you've got 1-volt process and 1.5-volt process and so on, do you do DC to DC conversion so that most of the power goes into the chip and not into the regulator?
Okay, so as you mentioned before, okay, if the cellular SoC, we have more than 30 different power domain, which means that we have a PMU, so power elements unit as an IC, and there's more than 20 or 30 DC switching regulator LDO. This is connected to the battery. That's right. And inside the SoC, they could, for example, there could be some 1 volt, 1.8 volt analog, 1 volt is a different analog. There's a lot of different power domain. But if you look into the SoC, maybe you can see the 20 different power rail coming from the PMU to the cellular SoC.
So the short answer is you do the power regulation on the main SoC.
That's right. Okay.
I would like to make a small update. It looks like the file is now up and running. Maybe it was just too many connections to it. So if people would like to give another chance for the download, the ICC02 is now broadcasting. And at least I can see the file.
So Okay, so now assume that now we have a FF silicon, FF silicon, because okay, for the traditionally we run the simulation for the SS because FF means now we have a fast silicon. SS means it's a slow property of the silicon, which means that we can run, for example, 1 gigahertz at the FF silicon at the low voltage, but when we have a SS silicon, we need a more high voltage. That's the reason we are assuming the worst case scenario all the time. So we assume that SS is silicon, so we are providing high voltage to meet 1 gigahertz per month. But sometimes if you have a silicon from the manufacturer, some silicon could be the TT and FF, which means that we don't need to actually apply the, for example, 1.2 volt, because 1 volt is enough. Which means that we are wasting some power by raising some voltage at the FF corner cap. So ABS means we can capture the process corner, like what is the process corner for each silicon? Is it FF or is it slow? So based on that, we can actually change the supply voltage like this, that we can save this amount of the power consumption. So this is called the ABS. And there's a number of the techniques. So here I like to introduce just two widely known techniques, which is called open loop ABS and the closed loop ABS. So open loop ABS is very simple. So it's measure the silicon property like a process kernel during the production time when the AT is the automatic test equipment and put the result into the one-time program memory. It's very simple and just a one-time calibration. So the processor is no software, the complicated, no software environment at the time, but there's a huge limitation. Meaning that we cannot capture the aging and the temperature variation during over time. So, and then next one is the closed loop ABS to tackle this limitation. So which means that you will keep monitoring the silicon properties over time, or just during the boot time, because sometimes you have a chance to put your smartphone. So when booting on, we can capture what is because of this aging issues, your property of the process will be changed over time. So we can capture this variation during the boot time, or based on the fixed interval over time. So we can capture the optimal operating voltage based on the aging temperature, but we need to develop a complicated framework to have this solution inside the smartphone. Okay, the second technique to tackle this PVT variation, which is called the adaptive, the break-even time scale technique. So this technique is mainly used to optimize the standby power or the idle power. For example, now assume that you have an application processor and you will have an L1 cache and L2 cache, and there will be some the external memory like LPDDR2 or 3, and the data can be transferred through the memory controller. Now assume that you have three different power modes. First is active mode, and these two are maybe you can call the low power mode, maybe or non-active mode. They could be Wi-Fi, simply the clock gating, the domain mode, simply just the clock power gating. When power gating, because we need to flush the L2 cache, totally the power of this whole application processor, which means that whenever AP enter the domain mode, we have to save this L2 content to the external memory through the memory controller. So you can imagine that there's a lot of some penalty overhead when we transfer a lot of L2 cache content to the LPDDR2 or 3 through the memory controller. It's an SoC. But if we compare the absolute power number between two different modes, because WF5 mode is just a clock gating, which means that there could be still a lot of leakage. Because current smartphone, if you look into the current trend of the application processor, you'll probably see more than one maybe 1 megabyte or 2 megabyte for the L2 cache compared to the small size one, which means that there could be a huge leakage power consumption if you have a fast silicon. So normal mode shows the low risk power consumption compared to the WFM mode. So what is the break-even time? So break-even time is the minimum length of the idle period to enter default low power mode. If you have a chance to enter either WFI or domain mode. So maybe this slide shows the explanation on the break-even time. So as I mentioned before, because of the process variation, process temperature variation, we need to capture this behavior, and we cannot use a single break-even time because a single number is not optimal for the other the silicon because of the radiation. Now assume that your phone is at 50 degrees C, for some by loading some video playback or video recording. So this is a break-even time. This is a break-even time for the typical silicon. This is a break-even time for the fast silicon. Now assume that we have 50 degrees C, and if we expected the idle period is more than like 0.7, then it's better to enter the normal mode. But if you enter the this is a break time. So this is a kind of a break-even point. So which means that AP is running, and and we can expect more than, for example, 0.7 per second or millisecond. It's better to enter domain mode, then we can save much power. But if you expected the idle period is less than 0.6, it's better to enter the WFI mode. If not, there's a penalty because, as I mentioned before, there's a huge dynamic power consumption because of the flushing the L2 cache, and there's a kind of some high switch activity in the memory controller. We can see the higher dynamic power. So this is a adaptive bring time to optimize the power consumption from the silicon or the maybe software perspective. So we can use this technique to tackle the PVT variation. So now it's so challenging. So this is how to analyze a workload of the mobile application with the smartphone. So this graph shows that how many frequency range we can use for each application over time. For example, now you can see the angle bar for your smartphone. You can see more than 30% of time we need idle. But if you have a certain amount of time, you need to have more than 900 megahertz speed, or maybe you can use just 500 or 400 megahertz speed from the application processor, which means that application processor already have like a dynamic frequency typing, which means that it can actually change the operating frequency based on the workload. But this is one example for, if you look into your smartphone, you already download more than 10 or 20 different applications. Maybe in the future you have more than 100. So it's really hard to analyze the characteristics of all the applications. Then sometimes, although we apply like 900 megahertz, it may be not optimal for the exact application time-wise. So we need to have some way to improve the decision-making strategy of a combination technique under some uncertain workload behavior. So here I'd like to introduce some technique so-called the machine learning-based the power management technique. This is a way to how to improve the decision-making strategy to minimize power consumption. The goal is to find what is the optimal voltage and the frequency level based on the workload. There will be several ways for the machine learning, like a supervised learning or some network, some vision. So here I like to use the supervised learning because it's very simple to implement and simple to analyze. This is a supervised learning is a technique to kind of to discover the relation between the input picture sometimes we can call the incoming workload and the output measure, performance or power. So simply the input feature affected the output measure in terms of the power consumption or the performance number. So the input feature is kind of a quantifiable feature which affects the output measure. Output measure is kind of a categorical performance or power the other way. But here I just define like incoming workload. As a result, it could be a different power performance number based on this. The supervised learning is used. Okay, mostly it used in some kind of a data center like some Amazon or Microsoft to capture the user behavior, to see what is expected the user behavior in the future. So they use the machine learning. But here we can also use this technique as a form of the power management technique inside the smartphone. So this is a way how to predict the performance in the power load system, and we can actually applying some dynamic voltage and scaling in advance to minimize power consumption. So when we have some different set of the workload, then by using the machine learning, we can predict the future behavior, and we can find out what is the optimal the voltage and frequency level for the process. So this slide shows how we can use the supervised learning for the power management. So there will be a so-called training phase and then the classification phase. So what is the training phase? So training phase, we need to extract the input feature and at the same time the output measure. So input feature could be some bandwidth, CPU utilization, what is the load, what is the cache mean, which will affect the power and the performance level of the system. So here's I use a simple metric for the power and the latency as the output measure in this example. Then there could be some training set collection. I will show the example later on slide. So there will be training set collection, like we can assemble this input and output measure into the table that we can call this is a training set. Then next phase is the classification. There is a number of types for the classification. For simplicity, I will use the Bayesian classifier to find out what is the expected level of the power and latency. And usually the goal is to find out what is the optimal the voltage and frequency level of the system. So this slide shows one example of how to extract input feature and output measure. And to better explain about this scenario, I simply used some queuing network. Like there's a test arrival into the queue with some type of the test, like high priority or low priority. High priority means this task can be go ahead of the low priority, and there could be kind of some low arrival rate of task or high arrival rate of task. And when the task arrival, what is the state of the queue? It's kind of a medium occupancy or low or high occupancy. And this is we call the input feature. Now what is the output measure? Assume that now you have the queue is full and you have still high arrival of task, which means that you have to increase the frequency to better to processing the task that we can see, otherwise the queue will overflow. So there's a reason you see the different level of the power consumption. So here the power can be like we can call the label. For example, the power 1 is could be the power consumption between, for example, 10 milliwatt to 20 milliwatt. The power 2 could be between 20 to 30 milliwatt. So we can put the label for the power similar to the latency in terms of the execution time. So this is a way how we can extract the input feature and output measure. So maybe you can see that why we have a different power level, or do we have a same input feature? Like it's a low priority task comes in, but at the same time the queue is a medium occupancy and the arrival rate is a medium. Same input feature, but power is different. It's a low power consumption and the high power consumption. What happened? Because because it's kind of a, if you consider the timeline, before this test, there will be some high priority and high occupancy and high data rate, which means that the processor is already loading the higher operating voltage frequency, which means that there will be some higher junction temperature, which will incur the higher leakage. So although the input picture chain still remains at high temperature, so if you consider both the dynamic and the leakage power, you will see the higher total power consumption. Now assume that now before this happens, we can see probably just a low priority, low Q occupancy, and low arrival rate, which means that we just see the low processing rate, which means that now we can see still just the low total power consumption. So when we have this type of the task, input picture, when probably see the similar range of power consumption. There is a reason, although we have a same input picture, there will be different level of the power consumption. There's a reason, and the other way, because of aging. Now it's the silicon learning over time, so silicon aging happen. There could be some voltage fluctuation and some temperature change. There's a reason, maybe 1 or 2 days later on, although we have the same input picture, we will see the different power level from the silicon. So there's a key aspect. The learning-based power manager can learn by itself about the output measure. So this is an example of the classification. So here I use the Bayesian classifier because it's very simple to use and simple to implement. The goal is to predict the expected class in terms of the power level by using just maximum output theory. And this is the equation for this Bayesian classifier. Now here's one example. Now assume that we have a new input picture with a low priority test, and at the time when the test input arrival, we can see medium Q occupancy and also medium arrival rate. Then what is expected the power consumption? So by applying this equation, so what is the probability of expecting the power one with this input picture? This is 1/6. What is the expected probability of the power 2 level with this condition is 1/12, it's like that. So you can see, okay, this is 1/6 is a higher probability. So when this input picture comes in, then we will expect this is a power consumption for the system. So we can predict the future behavior based on this classification. So actually there's because I skipped how we can achieve the optimal action because I didn't put over here because now you can capture power consumption. Similarly, you can capture what is the latency or execution time. Then probably you can capture this is estimated energy, and there's tons of technique to how we can find out the optimal dynamic voltage and technique. So maybe one way is to capture this is when you apply this voltage frequency, then maybe you can see the kind of a power saving compared to the expected energy. So now, from this slide, I will cover some summary challenge of solution. Okay, so there's a different aspect of the summary issue from the SOC and the flip-up perspective. So here I cannot cover all aspects of the summary issue, but here mostly focus on the SOC perspective and the flip-up perspective to how we tackle the summary issue during the design. So as mentioned before, high power means high power because the junction temperature is a function of the power density. This means we need to consider the die size at the same time. So high power density means heat generation. So now you can see because we are putting the billion of the transistor inside the single IC, and we can see the higher clock speed like 2 kHz for the AP. So we can easily imagine the high power consumption for the single SOC. Then we can see the higher junction temperature of the silicon. So then there's some limitation of the smartphone because we cannot put the some cooling fan inside the smartphone. So this is a kind of lot of limitation. Heatsink, cooling fan is not applicable to the mobile device. And so if you look into in your smartphone, there's a small PCB with a bunch of the IC which is packed into the decimal side because this is a form factor, limited form factor. There's a lot of limitation for the simulation. So and then because the user want higher performance, then we need to increase the frequency. But if we increase the frequency, you will see probably the higher junction temperature. So listen, if we don't have a thermal solution, there will be the performance degradation with some silicon lifetime or some reliable tissue. So, okay, first challenge is about some SOC perspective. So, before, maybe I'm not sure, some years ago, we didn't consider thermal issue for the silicon because we use like 16 nanometer technology or 45 nanometer technology with just the 1 gigahertz speed for the AP, and the LPDDR2 is around the 600 megahertz. Now we're expecting like a quad-core or sometime maybe in the hexacore with a 2 gigahertz speed, LPDDR3 maybe 4 with a 800 megahertz speed. Then we'll see, okay, how can we integrate into this kind of a limitation to SoC. So there's a lot of some packaging issue and design issue. So we need to capture the SoC level, the thermal solution at the early stage. So as I mentioned before, there is a package concern related to SoC. Now this could be some POP stands for package on package. This is a trend. Assume that we have a baseband SoC, and we can put the LPDDR to answer the external memory on top of the baseband. Because sometimes smartphone vendors they want a POP to minimize some area inside of the PCB or smartphone. So what will happen? So because the maximum junction temperature, limited temperature, living around 105 degrees C on the external the memory, which means that we cannot increase more than 105 degrees C for the baseband processor. Because this is attached here, if you increase the temperature, you will directly affect the junction temperature of the external memory. Which means that if you have a top package, then you will have a limited junction temperature baseband similar to the 105 degrees C, which means that we cannot increase high frequency, or which means that we respect the performance degradation. So, but if we have a LPDDR outside, kind of in the discrete format, we probably see in the 125 degrees C maximum temperature of the baseband, then we probably increase the frequency. But if you have a kind of a discrete, with wiring, then it's very hard to close the timing because sometimes we need 800 MHz speed between the LPDDR and the SoC. So these are a lot of some constraints based on what is the performance requirement and what is the package option. So the goal is to state this chip temperature within thermal fuzzy by using some technique which can cover from the implementation perspective to the application level. And there's a lot of technique by using the hardware-driven technique or some software-driven technique, like some adaptive thermal management, CPU hot probe, DVR-CAD, thermal via. Because the goal is to minimize the chip temperature, which means that we can minimize the power consumption. So power consumption, if you minimize power consumption, it could be some solution for the thermal management. But keep in mind that the goal of the thermal management is to maximize performance while guarantee the performance requirement. But goal of the power management is to minimize the power consumption under performance requirement or performance requirement. So there's a different aspect for the power management, the thermal management. So from this slide, I will explain from the simple to implement for the summer solution to the some complicated version from the SOS perspective. Now first, one is a stop and go. What is that? So now it's a SOS is learning. So we can define the two different threshold value, like some, for example, 85 degrees C and 105 degrees C. We can put the thermal sensor inside or external based on the design requirement. So when the SOS temperature increase, maybe hit the first threshold before the, okay, maybe if a high temperature means it's very risk to the silicon. So stop and go means, okay, if you hit the first threshold, we can just stop the CPU. Stop and go. This is a time and the voltage and frequency. For example, now it's running at 1 kHz. When the chip temperature is increased, so we can just shut down just the zero frequency. And when the chip is cooling down, then we can resume with the 1 kHz. So surely we can expect a lot of performance degradation over time. This is a simple technique to the stop and go.
Question. Has it occurred to the people designing these systems that another way to cut the power, rather than binary turn it off, would be to double the clock speeds? Obviously that won't promote it, but it could work with the applications. Just to make it run slower. I mean, have it. And that's an example of core.
That's what this whole system
He
is
does
based on.
say that to me.
Okay.
Oh, okay. Okay, so maybe I'll explain from the.
Fine, okay, I'm sorry. I see. What's the next slide? I'm sorry.
Okay. Stop and go is a very simple technique, but most companies are using this technique. This can be very old. We can expect a severe impact to the performance. Now it's a kind of some modulated clock, which means that now if we hit the first threshold, then we can use the modulated clock, because which means that there will be some clock-gating, but still running some application. But by running the some low power consumption, we expect the junction temperature will be minimized to measure kind of a regime in the clock-gating like that. Now it's kind of a more advanced, it's an adaptive DBFS technique. So now we can define some level of the different voltage and frequency, which is DBFS1 is a low frequency voltage, and DBFS3 is a higher frequency and a higher voltage radar. So based on when we expect the high temperature, we can lower the level of the frequency and the voltage. Then maybe still is running, but we can see a little impact to the performance. When junction temperature is decreased, then maybe we can use it with a high temperature, higher operating point. Then this is better than the old digital technique. So the other way is, so this is some comparison between the dynamic voltage, frequency scaling, and CPU half-clock. The DBFS is just run the lowest level of the frequency voltage based on the performance requirement. What is the CPU half-clock? Assume that we have two CPU. We can turn on one of the CPU depending on the computational requirement. Now assume that now we have two CPUs running with the lowest frequency, for example F. Now, by using the turning off one core, if you expect the same level of the performance requirement, then we need to have a 2x frequency level compared to this one. Now, what will happen if you running this scenario with a different the process corner and the chip temperature? Okay, this is a power consumption of the CPU. Okay, CPU 1 on. Okay. This is a CPU 1 and CPU 0, leakage and dynamic power, from this DBFS and the half-low at the low temperature, and this is for the high temperature. But because the CPU half-low, we turn off the one core, so we only see the CPU 0, the leakage, and the dynamic power. Because we increase the frequency double, we probably see the 2S dynamic power. but same level of the liquid, which means that at the low temperature, the CPU hot plug is better way to minimize power consumption. Now assume that at high temperature. So although we have a same amount of dynamic power number, if we're using the kind of a fast process called silicon high temperature, the piece is so high, which means that if you compare to the DBFS and the CPU hot plug, then CPU, I'm sorry, the DBFS is better way for the low temperature because of low power consumption. Sorry. High temperature, this is a hot plug is better way because the total power is much smaller than to the simple DBFS. So this is a kind of a, so maybe we can have some algorithm to choose which one is a better technique between the CPU hot plug or DBFS based on the process economy and the chip temperature. This is a way how do we tackle the PVT variation in the thermal management technique. So from the software perspective, we can use the predictive thermal management because this is becoming challenging in the smartphone because when we observe the junction temperature followed by the junction action, is too late to have some thermal control. So currently, a lot of companies are developing how we can predict the future chip temperature and doing some action in advance. For example, now we are running some the video playback at 1080p. Now we can expect the higher junction temperature. So then we can change the video resolution from the 1080p to 720p, or maybe we can apply the low some DBFS point that we can minimize power consumption, which results in the minimizing the junction temperature. So it's kind of a way to avoid the dramatic performance degradation. To build this production algorithm, there's a lot of way to build the model, especially with the mathematical formulation, like some Kalman filter technique or machine learning, like supervised learning, based machine learning, or initial value theory. There's a lot of technique, but we need to capture kind of overhead from the software perspective because if you have a code, it could be running on top of the application processor. There could be some overhead. So we need to consider this overhead compared to how we can minimize power consumption for each scenario. Then, as you mentioned before, the thermal manager, the goal of the thermal manager is to maximize the performance while guarantee the junction temperature. So if you have a separate thermal manager compared to the power manager, the rule will be very simple. First, monitor current status and estimate the future behavior, and then select the optimal deviate points to minimize the power, which results in the minimization of chip temperature. This is a technique from the silicon design perspective. We can actually put the thermal chimney or thermal via from the substrate layer to the high level silicon because we can dissipate the heat from the substrate to the ambient temperature or the top of the IC by doing the thermal via. So this is will have a large impact on the 3D IC. Now, second challenge is about from the platform level perspective. So as I mentioned before, we have a small size smartphone, and there's a lot of component inside the phone that we have some limited the thermal and the power constraint that we need to. So for this case, we need to capture some directly the usual behavior. Like some vendor, they have some limitation, like the skin temperature for your phone, maybe around 40 or 50 degrees C. And also there's some different aspect, like what is the skin temperature at the back side for the LCD. And we have some lithium-ion battery, the temperature limit as well. So the goal of the platform level is to how we remove the heat in a timely manner. This is a challenge for the platform perspective. there are several solutions for this level. It mostly focus on how fast it limits the heat from the platform by using some thermal interface material or heat spreader, EMI shear, and there is some material like some high conductivity thermal piece and TRT. So this is a solution for the platform level, now fancy from the some SOC level perspective. So here I'd like to introduce TRT, which stands for the temperature relationship table. This is a ACPI, the Advanced Configuration Power Interface. Is actually standard. This is from the ACPI model. So for example, the concept is very simple. Now assume that we have a process A and B and C, which is located very close to each other. Now assume that process A, B, C is running at the same time. So process A is getting hotter and hotter. How can we minimize the temperature of process A? Of course, we can minimize the frequency voltage to cool down the process A. The TRT concept means if we lower the temperature of the process B and C, it will affect the temperature of the neighboring process A. This is a concept of the TRT because we have some time constant for between each component with some values, so we can better utilize this TRT concept into the platform to better utilize some thermal management technique from the smartphone platform perspective. And as you mentioned before, the goal is to dissipate the heat as soon as possible. So thermal pass design is critical in the mobile design, and there could be some system change on EMI shear. This is a thin material and heat spreader. There will be the heat spreader, and so if you look into your iPhone or Galaxy phone, there will be some lot of thin material, thermal cap, or the heat spreader. This is a way to how we remove it in a timely manner. Okay, so now so far, because this is just a few examples of the some power and the thermal aspect. Still there's a lot of opportunity, but I didn't cover every detail of the power and thermal energy, but this is the most important thing, so I just covered these power and thermal challenges. Now is a wearable device. So during the last few days, you've probably seen the wearable as one of the keywords in the CES. So surely we have some technical session in the morning to see what is the forecast in the market of the wearable. So several months ago, GDP forecast around the 19 billion Indians by 2015, and there's a huge amount of opportunity for the wearable market, and there's a lot of challenges in this. Like how we the connection, how we minimize the power consumption. So wearable is not for just astronaut anymore. So we probably seen a lot of wearable from the CES before. There could be some blood pressure, wearable sensor, and calories, or some skin comfort, pedometer. So this kind of the way to monitor the person's activity, also by the sign. Maybe it can analyze by cells. Mostly you connect to the smartphone to analyze. Sometimes can be transferred to the cloud for the data analysis. And probably using this augmented reality by putting some eyeglass, I guess for the social perspective or contextual, commercial, and more. If you look into the, if you go to the grocery market by putting your, for example, eyeglass, you automatically calculate how much money do you need to pay for this grocery market. So this is one example of the wearable mobile device, like a Google platform. So there could be some OS component to do with the search engine connected to the API. Of course, there will be some functionality, like some shopping, a map, some payments through the NFC, like day, or voice recognition. This is connected to the API on top of the data processing. And these APIs can communicate with which is called the primary device or your smartphone. There is a huge amount of data transfer between the wearable device and smartphone. Imagine that you have some, for example, iWatch, Google Glass, or some Fitbit to check your calorie or there's a lot of some sensor. These are trying to communicate with your smartphone. So this is not simple to minimize power consumption for this. Okay, so data transfer is a key issue. This is one case study. So from between the smartphone and the Fitbit is a watch. This is a data rate during the maybe some 6 months. You can see 2x increase month to month by using the which is called the My Fitness Pal application program, by running on top of the smartphone, which communicate with your wearable. There's a huge amount of data rate growth between the wearable device and your electronic smartphone. So challenge is how to handle this large-scale data, at the same time how to maximize your battery life. Smartphone itself already has a huge data traffic because of the 2G, 3G, or LTE download data, and 1080p video recording, sometimes YouTube downloading, YouTube playback, reprising gaming. At the same time, if you have a wearable device, and then there could be some instant message through the, for example, iWatch to the smartphone, email checking, or camera, something like that. So, and then there's a lot of sensor in smartphone or some other type of the mobile device in terms of the light, proximity, touch, or accelerometer, gyroscopes. There's a huge amount of the data. So, how we can handle this large-scale data? For example, there's a sensor fusion. Some sensor cannot repeat again, right? Because when time passes, it's done, so we cannot repeat. This is some limitation. Also, there's some noise because of some magnetic sensor, so there's a uncertainty issue. So how we can play with this data, manipulate the data to get the information that we need actually. So this is a similar way how to improve the decision-making strategy of application under uncertain user behavior. From the smartphone data traffic, or wearable data traffic, we need to have some level of the context-aware mobile application. So there will be some artificial intelligence and the machine learning, automatic data mining. These are already employed in the some data center level of the application. Now we are having the terms of the wearable device. These are now moving toward into your smartphone to handle the large-scale data. This slide shows the one example of the mobile sensing. It's published last year. So we can have some 4 different phases, like how we collect the sensor data, and how we extract information from the raw data, and how we build the model and predict user behavior, and then we can construct the decision framework. There could be some issue during the sensing, like how we can sense the data, like adaptive sensing, and there could be some power issue, of course, the energy efficient sampling, data storage, and how we selected the best optimal classifier. And maybe we can use some simple or scalable machine learning. And then maybe it's kind of a short-term or long-term prediction. Some variable can be used by the some family, by the father or some kids. How we can find the best model from the multiple user, because there is some key usually using some kind of a play something like that. And how can we build this accurate decision-making framework? So this is a kind of an example of how we can handle the large-scale data. Now, from the power perspective, so we need to have some efficient data processing. For example, all of these wearable devices trying to connect your smartphone at the same time. Also, you already have some application learning on top of your phone. So how we can handle this amount of the data when you request from your wearable device. maybe you can upload some tasks into the nearby the cloud to optimize the power for the smartphone. So there's some research area like how to make the decision regarding whether or what computation you need to offload. Like a predict when computation will outperform execution of mobile device. Which means that if you wait some task while running some application, it's better to offload the cloud because communication power could be lower than the processing power of smartphone. So you can better send the data to the cloud, and cloud is a much better horsepower. You can process very quickly and send back to the region. So this is a way when we need to offload some tasks and decide which task that you need to upload to the cloud. It's a small size data or a bunch of the data from the smartphone to the cloud. And then wearable device or power management. This is one example. For example, now you don't have any wearable device. So you already have a single legacy power management, the engine in your phone. When you have a wearable device, you will have a sync with the primary phone. Then maybe your phone can be transitioned into the supervised power manager, which means that you have to check what is the power consumption for the wearable device. Because now watching that, now we have for example, the watch. If battery lifetime is exhausted too soon compared to the smartphone with the news for the application on the line. Same line. So the goal is to balance the battery lifetime for the watch and wearable device, the smartphone at the same time. So it could be the supervised mode. Then check what is the expected lifetime based on local. For example, now the phone trying to send, for example, 1080p video playback if user want to send video streaming through the watch. Then it's only know that what is the current state of battery capacity, what is the expected play time. So you can easily guess, okay, this is a lifetime of the battery. If you cannot see whole video playback, the smartphone by himself to check this kind of status, and maybe you can change the resolution from the 1080p to the 720p, or maybe you can play some kind of a buffering to be able to try. This is kind of way to supervise the power manager to interact with your wearable device to balance the battery lifetime, to extend it for the user the satisfaction. Okay, this is I'd like to introduce the one open platform for the mobile device. Actually, I already seen a lot of open platform during the CES. This is one example, which is called Wiki. So this includes the wireless connectivity, like Wi-Fi and the Bluetooth inside the platform that you can easily implement the software, and you can put you can connect to your client. That you can build anything that you want from this open platform to develop the wearable device or some wireless media device. Okay, this is the last slide. So summary. So I cover some challenges and the solution for the power and the summer from the smartphone perspective, and also I started to cover some challenges. So actually, there's a lot of opportunity for this segment. So hopefully, maybe you can get a better idea for your research or your segment. Okay, so this is collaboration with other team members, John, Redmond, Ajay, and Krishna. Okay, thank you.
Questions are welcome.
Do you use wind counters at all for temperature and process monitoring as part of your feedback for AUP?
Okay, so you mentioned that how we use the thermal sensor?
Thermal and process.
I'm sorry?
And also process monitoring.
Oh yeah, okay. Okay, actually, because I did mention about the process monitor. So simple way is by using the beam oscillator in the silicon to capture what is actually the number of the count. Because fast silicon will have some high number compared to the source silicon, so we can use a simply multimeter based kind of a performance monitor.
If you go back to slide 13, I think it illustrates the question.
17?
Yeah. There we are. Okay. So, you were talking about different parts of the device using different amounts of power. And you got down the corner, run fast, and shut down. So, my question is, are the differential thermal stresses across a chip small enough so that if like one part of the chip is a lot more than the other one, that is a geometry problem? Or is that a real problem?
Okay. So the forecast means
Like suppose that bottom corner expands more than the other parts of the chip. What does it do to the rest of the chip?
that is good question. So now because we can see the process variation, so across time. Now assume that we have some inside the silicon we can see like some higher fast or low fast, which means that we can see the process variation within die. So we call the within die the process variation. So then assume that we have a different power domain. So now we can put multiple like some ring oscillator based process monitor. We can put like some 16 by 16 or 4 by 4, or we can put like some multiple process monitor for each power domain, which means that we can better utilize based on capturing process property each domain, we can change the voltage at the same time for the different power domain.
Okay, it's last question.
Can you comment on the thermal chimney that you described? So does it mean that if you have an EMI shielded layer, you're reducing the amount of heat that's generated?
Okay, so your question is if we have a thermal chimney, then what is some effect on the thin material?
No, I mean you put EMI shield actually among the
Okay. You mean the EMI shield?
Yes. Does it have any effect on reducing the amount of heat being generated?
Okay. So the main purpose of the EMI shield to protect the kind of the signal noise from the other chip, because it's a kind of a small form factor. So for example, there's a lot of RF for the Wi-Fi, for the cellular. We have to put the EMI shield. But EMI shield also working as a kind of a heat spreader. So which means the main goal of the EMI shield to protect the signal noise, but also have a heat spreader. We can hit the fast compared to the other silicon. So what our currently trend is put the thin material first, and then we can put the EMI shield. Then maybe it's kind of the other material between the board and the top or bottom case of the result. Is that your question?
Yeah.
Okay.
Any other questions? Okay.
Yes. The main reason to use the multiple CPU because kind of as a market driven, but now it's kind of we are using dual core, quad core, and some company developing like some octa or something like that. Because the main reason for putting in more core because we have a lot of demanding application. Because user can work playing gaming at the same time downloading some video file and some something like that. This is not enough with the single core. This means that we put the more dual core or the quad core, or even although we have a dual core, maybe there are several types of the application processor like A7, A9, and A15. A15 is support to the high frequency, but we expect the high power consumption. But we can put 2 A15 or just 4 A9, which can provide us intermediate frequency level or low power consumption. So it's based on what is the segment of the market. It's a high end, like some Apple or the Samsung phone, or mid and the low end. Based on that, we can put dual core, high performance dual core, or just the medium quad core, something like that. It's based on what is the market needs, or what is the application do we need for the market. This is a kind of market driven to choose the number of the speaker.
Okay, I would like to thank Dr. Zhang very much.
Oh, thank you.
For